Good afternoon everyone and welcome to my presentation about the stability of the functional equation f of x y equal to f of x f of y plus g of x g of y plus f of x g of y on semigroup. My name is Karim Farhat and I am preparing my doctoral degree in applied mathematics with my thesis director Belaid, Bouikhalene and Idriss Ellahiani, Laboratory Limati, Department of Mathematics and Informatics, Polydisciplinary Faculty, Sultan Moulay Slimane University, Bni Mellal, Morocco. The aim of this paper is to study the stability of the functional equation 1, where G denotes a semigroup, f and g are a c-valued function on G, which G is a non-zero function. We note that C is the set of complex number. The case where G is a zero function, the equation 1 will write as f of xy equal to f of x, f of y, x and y in G. So in this case f is a multiplicative function. The equation 2 had been treated by G. Baker and G. Lawrence and F. Zorzito. See the reference 1 for more detail. The stability of classical functional equations are treated by many authors. For example, the stability of the cosine and sine functional equation 3 and 4 had been treated by L. Zekilindi. See the reference for more detail on nominable groups, and generalized by O. Ajbar and E. El-Qurashi on a nominable group with an involutive automorphism. See the reference 5. In this work we use some results of reference 1, 3 and 4. To begin we need some definition. Definition 1. Let G be a semigroup and the linear space of complex valued function on G. Then we say that the function f and g defined on G to C are linearly independent modulo T if lambda f plus mu G in T imply that lambda equal to mu equal to 0 for all lambda and mu in C. We say that the linear space T is two-sided invariant if f in T imply that the function x to f of xy and the function x to f of yx belongs to T for all y in G. Definition 2. Let G be a semigroup and M a function defined on G to C. We say that M is multiplicative function if M of xy equal to M of x, M of y for all x and y in G. Lemma 1. Let G be a semigroup f and g to function defined on G to C with G a non-zero function and T the linear space of C-valued function two-sided invariant on G. We suppose that f and g are linearly independent modulo T if the functions x to f of xy minus f of x f of y minus g of x g of y minus f of x g of y and the function x to f of xy minus f of yx belongs to T for all y in G. Then we have f of xy equal to f of x f of y plus f g of x g of y plus f of x g of y for all x and y in G. Proof. We'll let big F of x and y equal to f of x y minus f of x f of y minus g of x g of y minus f of x g of y for all x and y in G. As G not equal to 0, then there exists a y0 in G such as G0 not equal to 0. Therefore, big F of x and y0 equal to f of x y0 minus f of x f of y0 minus g of x g of y0 minus f of x g of y0, and while letting alpha 0 equal to 1 over g of y0 and alpha 1 equal to f of y0 over g of y0, we get the form of g of x. On the other hand, using the commutativity of semigroups G, we get this inequality. And by using the fact that f and g are linearly independent modulo T, and also T is a two-sided invariant linear space, we get this form of g of yz. And also we get this inequality. Then we obtain big F of xy and z minus big F of x and yz equal to alpha 0 big F of xy and y0 plus alpha 1 f of x and y minus alpha 0 big F of x and y0 multiplying by g of z minus f of x big F of x and y multiplied by f of z. Again, using f and g are linearly independent modulo T, and the fact that T is two-sided invariant linear space, we obtain big F equal to 0. Then the lemma is proved. Lemma 2. Let G be a semigroup f and g to function defined on G to C, and G a non-zero function. T be a two-sided invariant linear space of C-valued function on G if the function x to f of xy minus f of x f of y minus g of x g of y minus f of x g of y and the function x to f of xy minus f of yx belongs to T for all y in G. Then we have one of the following possibilities. Possibility 1, f and g in T. Second, f plus g multiplicative and g in T. Third, f equal to lambda square over lambda square plus lambda plus 1 m plus lambda plus 1 over lambda square plus lambda plus 1b, and g equal to lambda over lambda square plus lambda plus 1 m minus lambda over lambda square plus lambda plus 1b, where b is a function belongs to T and m is a multiplicative function and lambda is a constant. 4. F of xy equal to f of x f of y plus g of x g of y plus f of x g of y. Proof. If G in T, by using a similar demonstration of theorem in reference 3, we suppose that f not in T and f plus g is not multiplicative, then there exists y1 and z1 in G that verifying this condition, and after simple computation we have the form of f of x, since the function x to f of xy1 minus f of x f of y1 plus g of y1 belongs to T, then f in T that's contradicts the supposition, so f in T or f plus g is multiplicative. Then 1 and 2 of lemma 2 is proved. If f and g in T and f and g are linearly dependent, there exists lambda in C star and b in T such that f equal to lambda g plus b. Substituting f by lambda g plus b in the equation 1, we get the next equality. And by the hypothesis, the function x to f of x y minus f of x f of y minus g of x g of y minus f of x g of y belongs to t. Then we deduce that the function x to g of x y minus 1 over lambda multiplying by lambda square plus lambda plus 1 g of y plus lambda p of y multiplying by g of x belongs to t, and by using the theorem in the reference tree again, we obtain the form of f and g, then tree of lemma 2 proved. Now if f and g are linearly independent modulo t, applying the lemma 1, we get 4 of lemma 2. Theorem. Let G be a semigroup f and g two function defined on G to C, with G a non-zero function. The function x and y to f of x y minus f of x f of y minus g of x g of y minus f of x g of y is bounded if only and if one of the following assertions hold on. The first, f and g are bounded function. 2. F plus g is a bounded multiplicative function. G a bounded function. 3. F equal to lambda square over lambda square plus lambda plus 1 m plus lambda plus 1 over lambda square plus lambda plus 1 v, and g equal to lambda over lambda square plus lambda plus 1 m minus lambda over lambda square plus lambda plus 1 b, where b is a bounded function and m is a bounded multiplicative function and lambda is a constant that verifying this condition. 4. F of xy equal to f of x f of y plus g of x g of y plus f of x g of y. Proof. Let T the space of C-valued bounded function on G. Applying the lemma 2, we prove the necessity. If G is bounded function, then we get assertion 1 and 2, and the assertion 3 and 4 follow directly by lemma 2. Conclusion. In this paper, we have established the stability of the functional equation 1 on semigroups G. Second, we obtained some information on the nature of the solution of this equation. Reference, and thank you for your attention.